easy one, which is called the unit step function. This unit step function is an easier one because that's more physical and it's meaningful. That it is defined as 1 for t greater than or equal to 0 and 0 for t less than 0. This definition is by Oppenheim's book. And it's not a very accurate definition because of some problematic positioning or some positioning problems of its derivative. Its derivative will be the second signal. So the name of this one is the unit step. The more mathematically accurate definition is like this. I'll tell you in words. It's equal to 1 for t is greater than 0. It's equal to 0 for t less than 0. And it's equal to 0.5 at t is equal to 0. Okay, the transition, which is infinitely small, that transition point should be taken as 0.5 to be more mathematically meaningful. But this much is enough for the time being. It will be called the unit step. It's a step function, and the name unit comes from the fact that its measurement magnitude, this time its level value, is unity. It's 1. So if you try to draw it, quite simply, it's all zeros until the time axis to reach 0, and then at 0 it suddenly becomes 1, and it goes on like this. It's a step function. What can we do with this thing? For example, you may think of trying to draw u of t minus 5. U of, that would be an interesting thing, t over 2, or 2u of minus t sort of thing. Okay, the time transitions. Can you have any idea about what u of t over 2 would look like? It will be the same, because exactly from the origin it must be dilated or expanded with twice the value, but no matter what a t value for a positive t may be, it's the same for twice of it or half of it, so it doesn't change. So the expansion or squeezing of this infinite extent sequence or infinite extent function is the same as itself. But u of minus t is, of course, the flipped around version. Or u of t minus 5 is shifted towards right by an amount of 5. So this is the unit step function, and its name u of t is a commonly used term. That's why I'm paying a specific interest to this one. So from now on, you may encounter questions like the input to a system is u of t minus 1. So you have to immediately think that the u of t that I'm talking about is nothing but this one. Therefore, u of t minus 1 is 1 shifted towards right. So what is then u of t minus u of t minus 1? Let's call this x of t, the signal. Can you plot this? U of t is this, and u of t minus 1 is this, starting from 1. When you subtract that, the blue portions will cancel each other. 1 minus 1 will go back to 0, but here it will be 1 minus 0, and here it will be 0 minus 0. So 0 minus zeros are zeros, 1 minus zeros are 1s, and 1 minus 1 is again 0. So this is x of t, then, which is a box shape, sort of a signal. But what I'm trying to emphasize here is not this particular example. Instead, I'm trying to emphasize the name here. That is the unit step. Now, there's an interesting there's another interesting function named the unit impulse function, and its notation is First, let's write the name, unit impulse. We're going to use this unit impulse more in this course, throughout this course, instead of the unit step as the inputs. But it has some physical problems. What is that, first of all? It's the derivative, the time derivative of the unit step function, essentially. Can you think of the derivative of a unit step shape from here? An abrupt jump. Around here, the value, the derivative value is 0 because it is flat. Its slope is 0. Its slope is again 0 for all these values. Only around the transition, something is happening, and that happening is exhibiting a value of infinity, right? It's infinitely sharp, steep. So the derivative is infinity, which is something like this. Delta t is equal to infinity at t is equal to 0, and it is 0 everywhere else. But it's such a meaningless definition that we're not going to use it that way. And because of that meaningless definition, it's not physically possible to implement it. We can, we know that we have function generators, voltage supplies in the lab over there. And we have rectangular pulses, we have step shapes, which can be fed into a circuit. But this thing cannot be generated, so we cannot generate it and feed it to a circuit consisting of resistors, capacitors, inductors, etc. So why are we dealing with this then? We are dealing with this because you will soon see that it's mathematically more meaningful than it is physically. It has anything physical. It is going to be very easy for us to analyze signals and systems with respect to this strange function, impulse function. So we're going to do something very mathematical. It won't be physically implementable then. But in order to explain the mathematics, the equations and everything with respect to signals and corresponding systems, it will be very helpful. And let me give you the notation of the unit impulse. The notation of the unit impulse is an arrow. It's an upward arrow, relatively thicker than this axis, like this. And I'm going to put a 1 here. There is a meaning, or there is a reason for putting a 1 over there, and that's not because the value is 1 at 0. Of course, the value is infinity at 0. It's not 1. But it's the derivative of the unit step function, and it is different from the derivative of, for example, twice the unit step function. What's that twice the unit step function? It's 0 coming, and then it becomes 2 instead of 1, and it continues as 2. The derivative of that will also be infinity at 0, but these two functions are not the same. This will generate, in fact, this will be twice of delta t. So what is this magnitude then, which causes this one to have 1 delta t? That's why it is unit. We call it a unit impulse. It's because of the opposite of this expression. Let's try to express a unit step in terms of a unit impulse. Can we do that? I'm giving you this definition. It's something like this. The input comes into a system, and the output goes on, and the input, the system is taking the derivative of the input. It's a system. So when u of t comes in to this system, let's now notate the system like this. It's taking the time derivative, and the output is delta t then. Now I'm asking you the opposite, which is sort of an inverse system. Can we invert this system with S2, a new system, and get back to u of t. What is the inverse of this system? Meanwhile, we are now making an entrance to the inversion of the systems. This is a derivative. What's the opposite of a derivative? Mathematically, you should have some idea about that, right? Integral. So this system is supposed to be with this shape, an integration shape. Can we notate it? What is that thing which is the integral of the input? An integral will produce, if it's a definite integral from minus infinity to infinity, let's say, then it will be a number. But the input is a signal, so the output shouldn't be a number. It is supposed to be another signal. Let me close the door. Okay, so a derivative will also produce a function, but an integral is something like producing a number. We don't want to do that. So this is a little bit critical. The expression of this integral is a little bit critical. It is something like this. From minus infinity to t, we have to say. So it's not a definite integral in terms of some certain number boundaries, but this boundary, the top boundary, is the time index itself, from minus infinity to t. So what is the result of this integral then? It will be in terms of t. It depends on t. That's why it will be a function. So inside it, what are we going to write? So this is y of t is equal to integral from minus infinity to t x of we shouldn't say t, because t is already a parameter of the boundary. We must give a different name to that. Okay, just a name. Lambda, for example. That's a good idea. Let's call it lambda, d lambda. So this thing then will be in terms of t, this thing. Does it really work? From minus infinity to t, x of lambda d lambda. Let's put, instead of the input x of lambda, let's put delta lambda. Let's think of delta t. Let's take let's try to integrate delta t, which is this one, from minus infinity to t. Does it really work? Suppose that this is the then it will be the lambda axis, of course. T is the position until which we integrate from minus infinity to. Okay, for example, here. Let's choose t to be here. From minus infinity to t, integral of delta lambda. What is that? If t is here, 0. So I'm trying to find from minus infinity to t delta lambda d lambda with respect to t. So if t is here, then the value is 0. If t is less than that, it will be 0. It will all be zeros for all t's which are less than 0, for all negative values of t, right? Because the integration will give you nothing. How about a t point here? Now that is a strange, it gives us a very strange property of the delta function. The delta function has an area underneath, which is a finite area. Its width is 0, okay, infinitely narrow, and its height is infinity, so the area is 0 times infinity, ambiguous. But it's not ambiguous. This will also be explained in terms of a limit that we will explain. And the area, or the multiplication of this 0 and this infinity, is 1. The area under an impulse function is, by definition, 1. So if the area underneath is 1, when you integrate up to here, what will you get? 1 only, because all the others will be 0. They will not have any areas, nothing, no area after it as well. But at this impulse, we have a level of 1 as the integral. In fact, for all t exceeding the value of 0, the area underneath will include the impulse. So the area under the impulse is 1. Therefore, starting from here, immediately the integral will start providing us an area of 1. And it will go on as 1, 1, 1 everywhere for all t values greater than 0. So the area underneath will stay 0, and abruptly it becomes 1, and then it will continue as 1. That's how the behavior is. And as you see, with respect to this definition, this particular definition, in fact, these two signals are derivatives and integrals of each other, and differentiation like this is the opposite of the integration like this. These two are two inverse systems of each other. Now let's come back and talk a little bit about the area under the impulse. On this axis, I will start by this particular rectangular box shape, which is from minus half to half. This is the time axis, and the peak value is 1. Now, this is a rectangular box shape I'm drawing. And I'm going to give the name of this one to be dt. It's a function name. It's not a derivative dt or anything. I'm giving a name to this one. What is the area under this function dt? What is from minus infinity to infinity dt? Sorry about the ambiguity. What is that? It's the area under this box, and it's equal to 1. Now, what you really need to do in order to limit-wise approach to this delta t function from this dt is to make this narrower and narrower. And then meanwhile, you have to increase the height so that the area underneath will stay to be 1. For example, it may be from 1 over 4, minus 1 over 4 to 1 over 4, but then the height must be 2. And the area here will be the same as the area here. Okay? What we are going to do is we have to define a function like this. D sub epsilon of t is equal to 1 over epsilon d t over epsilon. As epsilon goes to or shrinks down to 0. For example, if epsilon is 0.5 or 1 over 2, then 1 over epsilon is 1 over 2, which is 2. So what is d of 0.5 t? It's equal to 2 times d 2t, which is this. So this function is, in fact, d 0.5 of t. It is half narrow and twice higher than the original one. Now, what we are going to do is, as you may guess, let me write it here. As epsilon goes to 0, we are going to make it infinitely narrow. The epsilon of t will be equal to delta of t. All right. No matter how narrow the width may be, the height will be with respectively larger. It will be 1 over epsilon. The height will be 1 over epsilon. This was the epsilon of t, as you may remember. So this is a limiting case. And that limit regardless of the value of epsilon, we'll always have an integral, the area of 1 underneath it. So the integral will always be 1. That is a limiting example, and as you see, since the height is abruptly large, like infinity, as epsilon goes to 0, you cannot generate it with a function generator or using electricity or anything. It's not physically implementable. It's not physically implementable, so why are we dealing with it? Why do we have this strange function? We will come back to trying to explain all signals with this strange function later for continuous time signals, because in continuous time signals it's a little bit problematic, as you see. But let me give you a hint. I'll try to explain any signal x of t, not necessarily u of t or delta of t or whatever you may think of, any signal in terms of delta of t. That will have a representation. It's a basis for me. Have you seen linear algebra? For those of you who have seen linear algebra, you know that you have some basis vectors. What are they? The trivial basis vectors are 1, 0, 0, 0, 1, 0, the Euclidean, and 0, 0, 1 in 3 dimensions. So any 3-dimensional vector, as we know, can be expressed in terms of these 3 vectors as a linear combination of these 3 vectors, right? Now, what I'm claiming is that these deltas constitute a basis for our signals. And we will define or describe any x of t in terms of delta t. But the basis, summations, etc., it will be a little bit different, of course. But that is the idea. And we will explain everything with respect to delta. And there will be a reason of that expression as well. We will come back to that. That expansion of any signal x with respect to delta is easier to explain in discrete time. So I will start by the discrete time. Usually it's easier to understand discrete time signals because we don't have integrals, we don't have derivatives, we don't have limits, we don't have anything. A discrete time signal is nothing but an array in the C programming language, for example. It's an array, nothing else. So what are they that we may think of? What are the discrete time signals that we may think of? Discrete time signals. I have previously mentioned about how to draw these discrete time signals, but let me start with an example, a particular example. This signal that we have are all zeros before this n index is less than 0. So it's coming from infinity. And then at n is equal to 0, it becomes 1. And then it continues to be 1. Like this. And can you give a name to this? Let's call it u of n, unit step function again. But this time this unit step function is in discrete time, and it's easier for our case. This is the 0 index, this is 1, 2, this is minus 1, minus 2, etc. And the values are all 1s after 0. Can you think of a corresponding impulse, unit impulse? So this is the unit step in discrete time. Notice my notations. You have to adapt to those notations because it's different from the continuous time. These are square brackets, not normal parentheses, and the index is not t or time, but it's n, which is an integer number. The corresponding impulse will be delta n then. And it is nothing but this. One impulse at 0. And all the others are zeros. So this is the unit impulse. And as you see, it's not infinity or anything. So it's easier to think of a delta n like this. Now, can we write u of n? So the question is this. Write u of n in terms of delta n. Okay, let's think of this one. How can we do that? Shifting and summing, probably, right? So u of n is, that's a brilliant idea. It's equal to delta n plus delta n minus 1, shifted towards right, plus delta n minus 2 plus delta n minus 3 plus etc. And it goes on. Now the question is then, can we really express this in a more compact way? Of course, it's an infinite summation. It's a summation like what? Let's call it k from 0 to infinity delta n minus k. All right. We can call it like this. Now, this has a strange similarity. Now, this doesn't have that kind of a similarity in its original form, but this is also equal to another notation, which is like this. K, this is a different k, so let's call it m from minus infinity to n delta m. Now, are they the same? They don't look the same, but if you think of the value of the outcome of this thing, you will see that it corresponds to the same thing. Why? Because now this one is in the form of an integral, just like the integral that we did over there for continuous time signals, for continuous time u of t and delta t, where the top index or the limit is the time itself, n. It was t in the integral, and inside it we had delta lambda. Now we have dm, or sorry, delta m, where m is starting from minus infinity and running up to n. Let's verify it numerically. What's the summation of all the values up to an n value, which is, let's say, minus 3, from minus infinity to minus 3? The summation of this function. It's not integral, then it's sample by sample summation. What is that? 0. 0 plus 0 plus 0 plus 0 plus 0 plus. It's all zeros. When n is equal to minus 2, it's again zeros. All zeros from minus infinity to minus 2. When you come to 0, to this point, from minus infinity to 0, the summation will become 1. Because all these values are zeros and there is 1, 1 here. And then, if you proceed further, for all the n values which are positive, the summation will be 0 plus 0 plus 0 plus 1 plus 0 plus 0 plus 0. So it will continue to be 1. That's why from minus infinity to n, delta m will be 1 when n is greater than or equal to 0, and 0 when n is less than 0. And that is the very definition of un, the unit step. So it is possible that we can express our unit step function in terms of delta functions like this that we have already seen. But this one now gives us, or it starts giving us an extra definition in terms of the samples. This is the basis representation that I'm talking about. This one is the same representation that we have already seen. But this is now more critical for us, because it shows us that as a linear combination of shifted and possibly scaled. By the way, all the scales are 1 for this case. So it's not, it doesn't look like being scaled, but they are scaled. It's a shifted and scaled impulses which forms a unit step function. Even for the unit step it works. For the other shorter signals, time compact signals, it will be even easier than that. For example, x of n is suppose like this. It is all zeros before 0, and at 1 it is 1, at 2 it is 2, at 3 it is again 1, and at 4 it is minus 1. Let's have some negative examples as well. It's always possible. We shouldn't think that all the functions are positive anyway. And after that, starting from 5, 6, 7, etc., they are all zeros. So it is 0 coming and 0 going signal. And in between, it has a compact support. From 1 to 4, the values are non-zeros. It's a finite extent discrete time signal. The question is, can we represent x of n in terms of deltas? And the answer is yes. X of n is equal to delta n minus 1, this one, plus, what is this? It is 2 delta n minus 2, because the value is 2, plus delta n minus 3 plus minus 1 times delta n minus 4. And this representation is telling us that as you can see, you must be convinced that any kind of a discrete time signal, if you have any kind of a discrete time signal, you should be able to write it in terms of shifted and scaled. This is 1, this is 2, this is 1, this is minus 1. These are the scales. Shifted and scaled impulses. Any function can be represented that way. And what are these values? This is 1, this is 1. This is 2, this is minus 1. Those values are the values that the signal has anyway. 1, 2, 1, and minus 1. Okay? And I'm telling you that u of n is this. X of n, for this example, this is an example we can say. This is the expansion. Can you generalize it? Can you write any x of n as a linear combination of impulses? What am I talking about, right? You should, maybe you're asking me this question. If you give me the example signal, I will be able to write it like this or like this. But I didn't give you the example now. So how can we do that? Well, I am implicitly giving you the example here. The signal is x. Just that assumption is enough. It will be an infinite summation. For all k from minus infinity to infinity, something like that. The value here will be x of k. We don't need a lambda or anything. It was necessary as an auxiliary variable in continuous time. Now the lambda is k here. It's not equal to n, as you see. Xk is the value of x at time index equals k. For example, here, what is this one? It is equal to x of 1. This x of n signal is here. And at k is equal to 1, x of k equals 1 when k is equal to 1, as you see. Because x of 1 is 1. This 2 is nothing but x2. This 1 here is x of 3. And this minus 1 is x of 4. So you don't really need to know what x of 4 is. Just say x of 4. That is x of k for all k's from minus infinity to infinity. And we're just multiplying it with a basis function, with a basis signal, like the basis of the Euclidean coordinate system. Delta n minus k. So this is x1 delta n minus 1 plus x2 delta n minus 2 plus x3 delta n minus 3 plus x4 delta n minus 4. Why didn't I write all the others from minus infinity to infinity? Because for all the others, xk are 0. So it is 0 times delta n minus 5 plus 0 times delta n minus 6, etc. They are unnecessary. That's why I didn't write them. But in general, we can write it like this. If xk's are 0 at some point, you don't need to write them. Let's come back to this example now. U of n is equal to this. What is that? We have u of k here. K from minus infinity to infinity, u of k. Let me write it like this. U of n is equal to k from minus infinity to infinity, u of k delta n minus k. U of k is 1 when k is positive or 0, and it's equal to 0 when k is all negative. Then for all values of k negative, we won't have anything. It will be all zeros times delta n minus k. So that's unnecessary. We don't have them. Starting from 0 and onwards, uk becomes 1. It's a unit step. So it continues as 1 values, as you see. So these will be 1. If they are 1s, we don't need to write them. That's implicit. And that is 1 times delta n minus k for all k from 0 to infinity. That's why we have this kind of a notation. But as you see, even this notation or this example is the same as this more general form of the expression of signals. This provides us with a very important conclusion. We are able to express any discrete time signal x in terms of shifted and scaled impulses. Notice that for a value of k is equal to, for example, 5, k is equal to minus 10, whatever. For a certain value of k, xk is nothing but a value. It's a scale. Here, xk is not a signal. It's a value. Because the k is some number, that's why x of k is a value. So it's like a. And delta n minus k, however, it is a function, it's a signal, because it's in terms of n. It's a variable. The time variable here is n, and k is the amount of shift of that. So this is a shifted signal, and this is a coefficient. It's a scale. Now we found a very fundamental observation then. We are able to write any x of n in terms of shifted and scaled impulses. For continuous time, the situation will be somehow similar, but it is more involved because the summations are usually transferred into integrations. Now, the quiz question, as for today's attendance, is this. And I expect you, most of you, to be able to write it. The question is as follows. Express delta of n, which is the unit sample or unit impulse in discrete time. Just a simple one. In terms of u of n. Write it in terms of u of n. That's trivial. It must be trivial. Then, if you are able to write delta n in terms of u of n, because we have written u of n in terms of delta n, in fact in two ways. The opposite is possible for this example. We can also write delta n in terms of u of n and comment on its similarity to the expression of delta t in terms of u of t. What was delta t in terms of u of t? It was the derivative. Delta t was the time derivative of u of t. Here delta n will be what in terms of u of n? First write it. Try to find a solution to that, and if somehow you feel that it is similar to the time derivative, write a few words about why that solution of yours is similar to delta t in terms of u of t, the derivative. Why is it similar to derivative? Or is it similar to derivative? Okay, that is your question. If you're, of course, unable to express delta n in terms of u of n, then you cannot comment on its similarity. But fortunately, you won't be evaluated with respect to that. But you have to do it because you have to give an answer and submit to the assistant, because that will be your attendance. So even if you cannot solve it, just write your names and submit, okay? Otherwise you will be unattended. Okay, we can stop the lecture at this point. We'll continue on probably Thursday.